Hello, it's good to be back with you, and I'd like to talk a little bit about derivatives. Now, derivatives are hopefully something you learned in college or maybe even in high school. Now, I'm going to go out on a limb here and guess that maybe you don't remember them as perfectly as you might. Okay, derivatives are the concept is about 400 years old now, and it may be possible that it seems like 400 years since you learned them. I'm betting that it's probably okay to go over a quick review of that, and that might help. Now, derivatives are central to optimization because we're going to be trying to slide downhill on functions in what we're eventually going to call function space. Well, if you're going to slide downhill, you're going to need to know what a slope is. Also, derivatives show up in most physical laws in the form of differential equations, and differential equations are just equations with a slope in them. We probably aren't going to use them in this class, but it's good to know they're out there and good to know that they're central to the world around us. So let's get on to derivatives. Now, some teacher somewhere, some professor maybe, probably drew something like this for you. And there's a curve there. So this is x, this is f of x, and this is a curve. Boy, this is pretty abstract. Okay, x is a variable, got that. F of x, what's f of x? F of x is a function. Well, what's a function? A function is just a relationship between this and this. We care about functions because they mean something. So think of them as like maybe a processor. If I push some number in, I get some other number out, and hopefully that number means something. Let's say I'm accelerating in my car. Okay, I have a little Kia, and let's say that this variable now is time. We could have written that as t, but variable is a variable. There's 26 letters, pick one, we'll use x. And that's the position of the car versus time. Well, that means the slope of this is the velocity. That actually means something. All right, it means I'm slowing down here. My position stops changing. My velocity must go to 0. So if this were time and that were position, this curve tells me where my car is, and through its derivative can tell me what its velocity is. This is handy. Okay, so derivatives are immensely useful in the things we're going to be doing in this class, so we need to know kind of how they work. So at some point in probably junior high school, somebody told you about a slope. Remember, slope equals rise over run? I'll get my head out of your way. There we go. Rise over run. Well, a billion years ago when I was in junior high school, those were the words they used. I don't know if it still is or not. I hope it is. But it's change in the vertical direction divided by the change in the horizontal direction. Okay, so let's maybe see what that looks like on this set of axes right here. There's x plus delta x. Okay? And delta x is just a change in x. So there's delta x right there. And it's pretty typical to use either a d, a little delta, or a capital delta to signify change in something. That triangle is a capital delta, the Greek letter delta. Why? I don't know. It's just it's tradition now, I suppose. Okay, so that means this number right there is f of x. That's this function evaluated at x. I have to erase this. I'm going to stretch this out a little bit so I can make this work. Go over here, and that's the function evaluated at x plus delta x. Those are just 2 points on that curve. So if I'm going to do this, I need a line to go between them. That wasn't bad, was it? Okay, that's the slope. That line there has the same slope, or is the slope defined by those 2 points. Okay, well, how would you write that out mathematically? This is it in words. And math is great, but it doesn't generally work very well when you try to explain it in prose. There was a time when people tried it. I actually read a very old book in which the author said x is related to y by the proportion of 1/3. That's an equation in prose. What he really meant was y equals x over 3. A lot shorter, a lot less ambiguous. So this is okay, but it's okay starting point, but we can't end there. Let's write this out in terms of mathematics. So rise is that minus that, change in height, okay? Okay, and run change in horizontal distance is delta x. That's a slope. That's a slope defined using that curve. Now, we've got a problem. Problem is, the slope I drew, that's not actually the slope of that function. It is in one place. It's actually in there. There's a point in between these two where the slope, this approximate slope, is the same as the slope of the function. But it's wrong everywhere else. If we've got a function that's wrong everywhere but one point, don't we want to fix that? That doesn't sound very handy. Well, how are we going to fix it? Well, the way to fix it is to move those lines closer together. All right, let's do that. I'm going to erase that with my finger here. Go all multimedia on you. There. Get rid of that. The finger's not that good. There we go. Okay, there. Let's move that other line over to here. And now, that's f of x. Okay, there we go. Now my slope that I draw, okay, is much closer to the actual curve. It just got more accurate. The error was reduced. Well, how do I reduce the error by an arbitrary amount? Let's fix this. Here, if you're taking screenshots or something, that'll look a little better. So the error is reduced if delta x goes down. The smaller delta x is, the closer our approximate slope is to the actual slope. All right, sounds like a plan. How small can I make this? I can make this infinitesimally small. Here's the idea. If there's a problem with calculus anywhere, it's that. As soon as you say the word infinitesimal, it starts to get confusing. Now, what infinitesimal means, it's an arbitrarily small number. It doesn't have any one value. You'll never know what delta x actually is. You'll never be able to write a number down. But what it does mean is it's as small as it needs to be without being zero. And that without being zero part is really important. And I'll show you here in a minute why that is. Ready? So I can make this arbitrarily small. Okay. So let's get rid of this. In fact, go from slope. We're going to go straight to a derivative. Okay, I'm going to start with this. I'm not even going to erase that. We're going to reuse this. Remember, that's just the definition of a slope. We're going to make one modification to it to turn slope into a derivative. And I'm going to write f prime of x, and that's df dx. Okay. Now there's more than one way to write down slopes because there were more than one person helped invent calculus or discover it, depending on how you look at it. There's more than one equivalent set of notation. And both of those will work. It doesn't matter which one you use, they mean the same thing. I am going to add one thing there. The limit as delta x goes to 0. Delta x does not ever become 0, but it gets as close as it needs to be. Ooh, okay. What does that mean? Well, give me the smallest number you want. Let's say 0.000000001. I don't care what number you give me. I can always divide it by 2. All right? So I can make this number arbitrarily small. When that number gets small enough, the error it creates is close to 0, right? And that's this limit argument around which calculus is based. Now, it took a while for people to wrap their heads around this. Let's take a historical aside. Archaeologists have found ancient fire pits, and I mean ancient, hundreds of thousands of years old, where there are animal bones with notches cut into them. Somebody was counting something. We'll never know what. Maybe how many berries they found that day, or how many goats they have, or how many fish they caught. Who knows? How many kids they've got. Something. They're counting something. So we have every reason to believe that math is probably hundreds of thousands of years old, at least in some basic sense. If it took mankind, say, 100,000 years to come up with this, and it takes you more than a day to get used to it, to wrap your head around it, that's okay. You'll get it. All right, so if the first time you hear this, if that makes you go, congratulations, that just means you're paying attention. Well, what do we do with this? This is all very abstract. Let's take this and let's work through a concrete example, or more concrete. I'm going to erase this stuff. And all this talk of functions and variables and stuff, let's make an actual function. Okay, this is not exactly concrete, but it's more concrete. Let's say my function is x squared. Well, what does that mean? Well, inherently it doesn't mean anything. It means something only in that that function now models something that's going on in the world around us. So maybe this is profit or speed or something. There's something you want to know about that's described by that function. So the abstract idea of the mathematical function becomes real when this models something you need to know. All right, let's say I need to know the derivative of that. Well, if you remember calculus from high school or college or wherever, you know to push that 2 to the front, subtract 1 from that so that you know that's true. By the way, did that feel like calculus or algebra? That feels an awful lot like algebra, right? Once you get used to the idea of a limit, calculus turns into algebra. Little idea here that very few math professors will ever tell you, but that's how it works. So how do I get from there to there? I can follow the rule that I learned, and I'm kind of doing it by rote. Where did that rule come from? Okay, so what I'm going to do is I'm going to push that function into that, and I'm just going to do what the math tells me to do. So my function is x squared, so I'm going to say x plus delta x squared. I put x plus delta x into that function, and that's how you write it out. And I'm going to subtract x squared. I put x into that function. I'm going to divide by delta x, and I have to put this in here. This is not optional, gang. I used to lose points in math class in college because I refused to put that in because I didn't really understand it. And I thought, well, maybe if I just leave it off, it's okay. Well, no, that's not okay. 17-year-old Mark didn't know that. Okay, so let's just do what the math says to do. Let's expand this out. We're still in the land of algebra here. This is probably 8th or 9th grade algebra. Let's just expand that out. That's x squared plus 2x delta x plus delta x squared minus x squared over delta x. Now, all I've done is I expanded that out right there and subtracted that from the end. This is just algebra, gang. That's all we've done so far. So let's see, x squared minus x squared. All right, let's just keep going with that. Limit as delta x goes to 0 of 2x delta x plus delta x squared over delta x. Dot there. All right, well, that and that cancel out. All right, I'm going to run out of room here. If you don't mind, I'm going to erase this, and I'm going to continue this up here on my little whiteboard. I like being able to do this in my office. It seems welcoming and comfortable to be able to do this, so hopefully you don't mind this little space on my whiteboard. We'll use this a lot. So let's write down what we've got so far. Okay, that's 2x plus delta x. So far, all we've done is algebra. We haven't done any calculus yet. When we apply that, that's actually calculus. Well, here's the thing. As that goes to 0, this gets arbitrarily small. Arbitrarily small. That means as small as it needs to be to be negligible. So that goes to 0. And what you get is 2x, which is what we knew. Okay, this is where that rule came from. Now, let's think about this. Wrote this down. This is the definition of a derivative. We went from here, algebra, 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 and then calculus. When we applied that limit, it became calculus, but it was only one step. Now, you can put any function you want into that rule, that definition, and the answer you get is going to be the derivative. Okay? Now, mathematicians have generalized this so that it works for all kinds of functions, and we'll learn these in the form of chain rules and multiplicative rules, product rules, quotient rules, things like that. So generally you aren't really doing that in your head, you're following the rules, but this is where the rules come from. Once you get the hang of this, okay, what that limit is, you jump from algebra to calculus. And it's all pretty straightforward once you have that idea. So there you go. We're going to go through the same calculation now in MATLAB and Mathcad. Okay, here we are back again in Mathcad to look at derivatives. And I'm going to just do the simple example we just did on the whiteboard. Now I'm going to define a function f of x, and I'm going to call it x squared. So that's x and then the up arrow and 2. Okay, just so we know we have it, there's a plot, and there's x, and there's f of x. There's the plot. Now, maybe some grid lines would be good. And again, I'm going to put the gray grid lines on it. Okay, so there we have it. So we know f of x has been defined because we're able to plot it. There it is. No big surprise there. Now, let's say I want to make another function that's the derivative of f of x. Well, I need to call it something. I'll call it df of x. And I'm going to have to define it here, but I don't want to have to do the derivative myself. I want Mathcad to do it for me. So I'm going to go up here to the calculus toolbar. And by the way, if you want to know how to turn toolbars on, hit View. See those toolbars? The ones that are checked are the ones that I have on right now. You can check whichever ones you want. Another thing is there are shortcut keys for most of the features in Mathcad, or many of them, I guess. I learned Mathcad a million years ago before there was such a thing as Windows. Hard to believe, but there you have it. I learned it on DOS, and in those days you didn't have any choice but to learn all the shortcut keys. Well, they haven't changed over the years, so I still have some of that knowledge lurking around in my head. If you happen to know the shortcut keys, good for you, and if not, don't worry about it. It's not important. You can always do things with menu picks. So what I want to do here is select the derivative, okay? Derivative with respect to x, and derivative of what function? Well, I want f of x. So there you go. Now, does that exist? Well, let's check. I think so. One way to check and see whether it exists, just try to put a number in it. Oh, there. Okay, there it is. So it does exist. Well, what does it look like? Well, I'm going to highlight that, and if I hit a comma on the keyboard, right, it gives me a place for another function. So there it is. I'll do that, and there. That's kind of small. Maybe let's make that bigger. There. Okay, so the red solid line is my function, and the blue dotted line is my derivative. And I can change all this stuff. I go up to traces. If I don't like a dotted line, I can make it a dashed line, perhaps. There, just to show you that you can do that. And again, these lines are pretty rough. This is the graphing algorithm in graphing routine that's in Mathcad version 15. Okay, so this is hopefully going to be fixed in Mathcad Prime 5. It's probably fixed in Prime 4, but there are some features in Prime 4, some plot format features that don't exist yet. So we're still using the old version 15. So here you go. There it is. Now, when we're going to want to find minima a lot, and the minimum of this red line occurs when the slope is 0. Well, that's the slope, and the slope, it goes through 0 at x equals 0. So there's the function, there's its slope, slope goes through 0 at the minimum. So there's the example in Mathcad. Okay, here we are in MATLAB, and we're going to plot the same two functions that we plotted in Mathcad. And in MATLAB, we're going to use the symbolic processing tools that are built into it. Now, MATLAB and Mathcad use the same symbolic processor, a program called MuPad, M-U-P-A-D. In fact, you can run MuPad directly within MATLAB if you want to. If people are interested, I can make a video on that later. Now, MATLAB distinguishes between floating point and symbolic variables in a way that Mathcad does not. So if you want to work with symbolic variables, do symbolic processing where you're pushing letters around instead of numbers, you have to tell it that you want certain variables to be considered symbolic, and the way you do that is you type in the command syms, and then list your variable names. So I'll say x, f, and df. So there they are. Now I have to tell it what my function is. So just like before, I'll type in f equals x squared and hit return. Because I didn't put a semicolon at the end of that, it echoes to the screen. And this right here is a function. It is not a list of numbers. I can evaluate this at any point I want, and it'll give me a number back. So next thing I want to do is I want to define the derivative of f. And the command is diff. Differential and derivative get used interchangeably. So I can say f, and since there's only one variable in it, I get 2x. Well, it's good to know that MATLAB and Mathcad agree with what we got on the whiteboard. Let's say I want to plot these. It's hard to plot that, so it would be more convenient if I did this. If I defined the function df as that differential or derivative. So I did. Now df is that function. Remember, a and s is just a dummy variable. It gets used when you don't specify a variable to assign a result to. So it's up there. I probably could have plotted that actually. Now when I want to do that, to make the plot, there's a command called EasyPlot that is just what you think. It's a very simple way to make plots on the screen. And the nice part about MATLAB is when you type in a command, wait a second, a lot of times it'll come up with all the available syntaxes for you. Okay, so I'm going to use that. I think the FUN stands for function. So I'm going to do that, and I want to plot from -10 to 10, just like we did in Mathcad. So I'm going to do that, and there it is. Now I want to plot the derivative on there as well. So to do that, let's start by moving this over and making it so we can see both windows here without one overlapping the other one. There we go. Now, if I want to plot a second curve on that, I have to tell it that the next plot command doesn't generate a new window. It's actually supposed to go on that window. So there's a command called hold. I'm going to turn the hold on. Looks like hold on. Hold on, which means hold that plot. I'm about to put another curve on it. So there you go. Now I want to plot df on that those same axes. So I'll hit up arrow once, up arrow twice. That recalls that command. And I'll just put a D there, and I can hit return. I don't have to put the cursor at the end of the line. And there it is. Well, that's nice. Maybe I want grid lines, so I'll type in grid. There it is. Now I've got the grid on the plot as well, and it showed me the second. Right there's the second function that it plotted right there. And again, where the function goes through a minimum, the slope goes through 0, just like before. And I can modify this plot in any other way I want. I can add labels. I can do all the things that MATLAB allows you to do. Now hold is still on. If I were to execute another plot command, another function would go up there. Well, if I don't, it's good form to turn the hold off. Let's do a little housekeeping on your way out here. So there you have it. There's the same set of functions calculated and executed in MATLAB using symbolic processes. I hope this helps. We'll talk to you next time.